mapping of inputs to outputs.
Yes. Are there any specific like restrictions we have to watch for those mappings?
Each member of the domain maps to exactly 1 point.
Yes. And so to kind of maybe break that out in not specific terms, what we want to make sure is that if I have a function, like let's say we have an equation here, 5y is equal to these things. If I'm able to plug in an x and get a single y, I have a function. If I plug in an x, let's say like a 2 here, and then that gives me the result of, oh, y can be 4 or y can be negative 100, we lose that definition of a function. We don't ever want to plug in one input, typically an x, and get more than one output. And so typically start representing functions in this kind of point notation of saying, okay, my input is -1. I don't know what my function is. I don't know the graph. I don't know the equation, but that's fine. That actually makes my life a little bit easier. But this is my input. My input here is -1. I get an output of 2. My input here is 2. I get an output of 2. My input here is 7. I get an output of -5. And so essentially what I'm going to look for is if I'm checking to see a function, I want to make sure that every single value in the front is going to a single value in the end. And so let's see here, what's happening. We have 7 goes to -5, great. We have 2 goes to 2, so we're covered there as well. But here I also have -1 going to 2. And so this first example is not a function. And the why of it is that we have this -1 going to 2, and we have this 2 going to 2, which is a big no-no. You can't have two values of the domain, two different values of the domain going to the same output. What about this guy? Oh, no. Sorry, this is a function. Now everyone's going to be confused. Apologize. This is a function. And so the shortcut actually with a function is, for starters, we go through the inputs. And if I have different inputs, like here my input is -1, here my input is 2, here my input is 7. So I have 3 separate inputs. There's no way that I'm going to have 2 inputs going to 2 separate outputs. So it's a function. And if you want to be very specific and show your work, you would say it's a function and then maybe state the definition. Or honestly, a good justification is, well, we have 3 different numbers for inputs. None of them match up, so we're not worried about breaking that definition of a function. Okay, now with that terrible explanation, maybe that will actually help us understand question 2. Is question 2 a function?
No.
No.
Why not?
The 1's going to -10 and 4.
Yeah, so this is the issue here. This is what I was kind of getting at with the first question, but I had flipped them in my brain. Make sure you don't flip them in your brain. Is that I have 2 or a single input going out to 2 outputs. So 1 is getting mapped to -10 and 1 is getting mapped to 4. That's the issue. I'm having this one input that is going to 2 separate outputs. That's not okay. And honestly, if you're looking for a justification, again, you could just write this. You could write the 2 points, I'm fine with that. Or you could say, okay, 1 is getting mapped to these 2 separate outputs. Something like that. Honestly, this question will probably show up on the exam, but it's probably going to be like a all or nothing type of thing. So a small justification is a great idea, but if you're saying it is a function and it's not, or vice versa, you're probably going to have a hard time getting some partial credit on that. Okay. So again, that's kind of the shortcut. If I have 3 different values for my x, -1, 2, and 7, I'm not even worried about following this definition. It's going to be a function. There's no way one single input is going to 2 separate outputs. Where if I have 2 of the same x values right here, 1 and 1, then my brain should start to have a little bit of an alarm saying, oh, that's probably not good. because I want to avoid single inputs going to two separate outputs. And so it's probably not a function. Here it's not, because of specifically one goes to -10 and one goes to 4. But that's actually not always the case, which might lead us into this question. What do we think about this last guy? It should be number 3, but it's a table. And so we typically see functions being represented in 4 ways. One, this layout here of x to y, x to y, x to y. In a table, very similar actually, except for we usually say, okay, my input's this guy, my output's this. So it's very much like this list method. Sometimes I see equations, sometimes I see graphs. Okay. Question 3, is it a function or is it not a function?
Not a
It
function.
is a function.
I hear not, I hear it is. Who wants to justify their answer?
The -2, 5 is a repeat, so it's the same point.
Yes, and so this is a trick question. Like I said, when you see 2 matching inputs, 2 of the same inputs, alarm should go off in your brain. You should say, oh, that's probably not a function, but let me think about it further. So I see 2 -2s. Well, then I look at their outputs. -2 is getting mapped to 5, and -2 is getting mapped to 5. So the inputs are being listed twice, but the output's the same. And so we usually don't represent functions like that, but we can. And it's a function. Well, it's sure, I have 2 of the same inputs, but they're being mapped to the same output, so I'm covered. I don't know why it's not letting me tab. So, is that somewhat clear? I'm sorry for the confusion, but we will see the definition of a function 1 or 2 more times. And well, it's in the video, and we'll practice it. So any questions about this? Great. And to emphasize again, maybe it'd be a good idea on your note card to have kind of an example of this is a function, that is not, this is not a function, and some explanation as to why. Hint, hint. Okay. Now, as I mentioned, sometimes we have a table, sometimes we have this, I believe it's called list form, sometimes we have a graph, sometimes we have a an actual equation. And so for starters, before I try and kind of justify whether or not something is going to be a function in the form of an equation, I'm going to solve for y. Kind of similar to what we did with the equations of a line. I want to get the y by itself because, well, it made graphing much more doable. Similar here, if I want to determine if an equation is a function, I should probably solve for y first, because then I can kind of clearly see, oh, I'm going to have more than one output, or I'm going to have a single output. So solving for y, how do I do it here?
Divide both sides by 5.
So what's my answer going to be? At least the simplified form of the equation, I guess.
Y is equal to x minus 1.
Sure. And so if I divide by 5 on both sides, I'm going to divide the entire equation. So I divide the 5x by 5, making it x. I also have to divide the 5 by 5. So make sure you're doing that. When you're dividing both sides of an equation, you have to divide the entire side of the equation. And so this explanation, again, is going to be a little bit tricky. It might be a little bit more illuminating when we get through this question. But, well, this is an equation of a line, right? We could go about graphing this. The y-intercept is -1. The slope is 1. That's not really what this equation is asking for, but we could graph it. And so to think about that, if I plug in a value for my x, well, it's a line. So I'm always going to get a single value of y. So this is also a function. So if you're able to get an equation of the line, it's a function. Lines are always functions. What about this guy? I want to solve for y.
You'd add 1 to both sides and then square root both sides of the equation.
Perfect. So add 1 to both sides, square root the equation. Is there something I have to be careful when I'm taking the square root of an equation. Both sides of an equation, I guess. Think back to when we were doing equations with square roots, or like we did this a lot when we were completing the square as well. Is there something I have to do when I'm taking?
Wouldn't it be y equals plus or minus the square root of x minus 1?
Great. Now, this is not a function. Does anyone have a reason why that might be the case? Or possibly an example. Examples are great ways to say, oh, this is a function or this is not a function. It's a little bit tricky. Give you a little bit of time to think about it.
Because it doesn't graph as a line, it would be a parabola.
You can have graphs that are not lines and functions. But I like where your head's at. Wait, did I say that right? You can have graphs that aren't lines that are functions. Yeah, I think that's what I said. Any other thoughts? Again, it's a little bit strange. It's kind of a bit of a stretch of a question, but this is a function. And the reason why here is this guy, this thing that we just talked about, right? It makes sense. If I plug in, let's say, for example, 2 for x. If I plug in 2 for x, 2 minus 1 is 1. Square root of 1 is 1. And so I would get a value of y is equal to positive 1 and y is equal to negative 1. So I'm getting 2 separate outputs for a single input. So this is not a function. And you could say, you could provide an example. Say 2 maps to, maps to 1 and 2 maps to negative 1 if you really want to. But the shortcut for this class is, because it's very kind of hard to throw any function at you and make you kind of determine if it is a function or it is not. This should be the red flag for you. If you're solving an equation and you get down to this plus or minus something, it's not a function. And it's because of that short justification. If you want to write out that short justification, that's great. But that's the thing you have to watch for in this course. There are other equations that are not functions, but for the purpose of this course, this is going to tell you it is not a function. Otherwise, if you have something like this, or even if you had like the cube root of something, no matter what you plug in, you're still going to get a value of y back. So that's the shortcut for this course. Again, that's not for every course, but for this course, that's a perfectly fine way to think about functions or not functions. Do I have this weird plus or minus in front? Oh, it's not going to be a function, well, because I could get 2 outputs versus honestly anything else. Any questions about that? Of course, my math lab is mean, so I can't speak for the entirety of the homework, but for anything we'll see on the exam. Cool. Yeah, so that is a very kind of particular definition. The course captain, the person in charge of this course, really likes the specifics of that definition. So be aware of it. It is just very small and very specific, and honestly doesn't feel very mathematical, but it is very important. And we'll see a fairly similar definition in a couple of sections after the exam. Okay, let's go through one more thing before I let you loose to practice these concepts. And this is function notation. And so when we deal with equations and we only have one equation, we're kind of used to this. It's perfectly fine to just say y is equal to x minus 1. There's only one equation I'm talking about. So if I reference an equation, you're going to know exactly what equation that is going to be for that problem. But that's not always the case. Sometimes we have a lot of different functions. Sometimes we would have y is equal to 3x plus 2, and then the next equation could be y is equal to 5x minus 1. I could give you like 10 equations. And then if I say plug in 5 into your equation, you might say, oh, wait, which one? I have 10 of them. I don't really know which one you're talking about. And so sometimes when we have so many different equations, we like to name them. So that's where this function notation comes into play. I want to name my function so that later on, when you tell me things to do with it, if you want me to plug in values, if you want me to add it to a different equation, I'll be able to kind of decipher and say, oh, that's the F equation. No, that's the H one. That's the G one. And so all this is telling me is the first thing is the name of my function. Capital F in this case. F shows up a lot because, well, function. G shows up a lot, H shows up a lot, but like any letter works. It doesn't have to be F every time. And this just tells me what my input is. What value am I going to plug into my equation, or what variable am I going to plug values into for my equation? So that's all this means. Something to watch for is that this looks a lot like, to a lot of people, including me, that, oh, it's F times X. Because that's honestly the exact notation that we see when we are multiplying X by a variable. But just watch for that. If you have a single F times X on one side of the equation, it's probably actually not multiplication. It's just saying this is a function. This is a really weird way to essentially write Y. So when you get your answer, don't try and multiply it or do anything else to it. And so to see it in practice, I can say, okay, my function is f of x is equal to 3x plus 1. I want to find f of negative 1, this first thing in question A. Does anyone know how to do this?
You just replace both x's with -1.
Yep. And again, this left part is just notation, so I'm not actually going to do anything to that side. But I will replace the -1 on this side and then just do a little bit of simplification. 3 times -1 is -3. And then that is going to be equal to -2. So this is called evaluating. So when it's asking you to evaluate an equation, that's what we're doing here. We plug in a value and then we do a little bit of simplification. We do a little bit of arithmetic. Okay. How do I do B? Because that seems weird, right? Like we have a number, and that's honestly for the most part how we deal with functions is we plug in a value, we evaluate, and we're good to go. But that's not always the case. Here I don't have a number, so what do I do?
For the first one, the answer, would you write like f of x equals -2?
You could. Technically, the correct way to write it is this. I would accept either. If you write f of x is equal to -2, I know what you're getting at. So,
Okay. Thank you.
Good question.
You'd still just plug it into the equation, no?
Yeah, exactly right. It's going to feel a little bit weird because we're used to kind of dealing with numbers, but exactly right. When we're dealing with function notation, if we have something inside of this parentheses, all that's telling me to do is say, hey, pull down that equation, that function, take that 3x plus 1, and, well, replace that x with a plus h, whatever is inside this parentheses. And then again, I have to do a little bit of simplification. In this case, I would distribute the 3 to both terms and get 3a plus 3h is equal to 1. Which again feels weird. I'm used to kind of getting nice number answers, but this is algebra. That's going to happen a lot. We're going to have answers that are just variables. That's fine. And again, you could write f of x is equal to this if you wanted to. You could write this. I'm fine with either one. And so we can't get into this habit of, oh, every time I have a function, I know exactly what I'm going to do. I'm going to throw in this guy into the function and I'm going to simplify. Yes, again, that's what we're going to do the majority of the time, but not all the time. This one looks a little bit different. So what's different about this one? Or maybe if you know how to solve it, that will help us understand what's different about it. What's different about C versus A, B, and honestly D in this case?
It gives you your f of x value
Mhm.
instead of having you solve for it.
Okay, so then what do I do?
You would plug 13 into the f of x instead of just plugging it into the parentheses.
Yeah, exactly right. So here I had a parentheses with something inside of it, so I plugged it in and did arithmetic. Now in this question, I don't know what my x is, right? It's just still an x. So I can't really plug anything into my equation. But I do know my output, my result is going to be 13. So I plug in 13 into my equation for f of x now. I replace that. I know what that value is. And now I'm going to go about solving for x. How do I do that?
Subtract 1 from both sides and then divide by 3.
Mhm. So here I get x is equal to 4. How could I check this answer?
You plug it back into the equation to make sure that when x is equal to 4, it equals 13.
Exactly right. Well, this is my input that would force 13 to happen. So if I wanted to check my answer, I just plug in 4 into my function. I should get this result of 13. How do I do question D?
We just multiply both sides by -1.
Sure. Is there something else I have to do?
I have to replace x with b.
Yeah. This is a little bit of a two-parter. But the new part is what John was describing. So I have f of -b. So I have to do two things here. I have to, for starters, plug in b for my input because it's not x anymore, it's b. So that's not going to really be a big change. It's just instead of an x, we have a b over here. Whatever, it's slightly bigger. What John was also talking about is here. I have this negative in front of my function. So if I have a negative in front of my function, what I'm going to do is I'm going to multiply the entire other side by -1. Or another way to think about it is I'm going to flip the signs of the other side. So my final answer is going to be what?
-3b minus 1.
Mm-hmm. Any questions about this? Great. Breakout rooms. So this is section, I think 3.1 part 1. There might be a little bit of part 2 in it. I forget where the breakdown happens, but that can be found in Canvas. Yes, so I have my f of x, or I have my function f of x. I'm plugging in my x plus h for x, replacing that. And now I have to do a little bit of simplification. So I'm going to have to FOIL out my x plus h. I've done it so many times. It's just x squared plus 2xh plus h squared. For the sake of time, I'm just going to throw it out there. You would on your own probably have to do that. X plus h times x plus h is going to get you this if you FOIL it. And then +1 still going to hang out there. And then I distribute 3 to here, 3 to here, 3 to here. And I get this 3x squared. 2xh times 3 is what?
6xh.
Yep. And h squared times 3 is 3h squared plus 1. Everyone good so far? I did a little bit of fancy algebra, but nothing too shocking. We know how to FOIL stuff like this. Everyone good so far? Great. And so looking back at this formula, I want to find all of the pieces. I want to find this guy. Well, I just did that. I actually already have this guy, right? What's my f of x?
3x squared plus 1.
Yeah, I start with that. So I don't have to do any effort to find that. So that's one piece. My other piece is this. And then, well, the h is just h. I don't really need to put any effort into finding that. I'm just going to plug it in. Whoops. So I take this equation. My f of x plus h is what I just found. That's always your first step. Find your f of x plus h. It's this guy. So I replace this. 3x squared plus 6xh plus 3h squared plus 1. I know what my f of x is. We talked about that. That's right here. Plug that in as well. Make sure you put that in parentheses because otherwise you might not distribute your negatives correctly. Everyone good with that? A lot of things just happened there, but really at the end of the day, all I did was take what I found here, put it in here, and then took my function, put it in there. Nothing else. Everyone good with that? Great. And now, while I simplify. Step 1, maybe it doesn't really need an entire step. I'm going to flip both sides here. That's subtraction. So I have a negative, so I'm going to make sure the negative goes to both terms. So I'll have a negative 3x squared minus 1. Nothing too shocking there. And now what happens almost every time is a lot of things cancel. So what cancels in this step?
3x squared and the 1.
Mm-hmm. So 3x squared cancels out. Those will go away. And then I think you said the 1 as well goes away. Yep. I have a negative 1 here, a positive 1 here. So I'm left with this. Now, one of the cool properties, okay. One of the cool properties that happens with the difference quotient is that if we've done everything correct in the second to last step, we should be able to cancel out this h on the bottom. Or another way to think about that is every term up here should have an h in it. And that's always the case with the difference quotient. Again, the reason behind that is a little bit more calculus-y than we need to talk about in this course, but that's always going to happen. So if you aren't able to cancel out an h out of every one of your final terms, you probably did something wrong. And most often it's this, you didn't flip the negative on both of them, but also probably the second biggest cause is finding our f of x plus h. So that's really nice. We have a way to quickly check to make sure that we at least are on the right track, that we have these h's canceling out. So if I divide 6xh by h, I'm just left with 6x, and then 3h squared divided by h gets me what?
3 squared.
3h. So the h doesn't go away. It's just I have two h's, I have h squared, and so this is going to cancel one of them out, giving me a 3h. A lot of stuff happening there. Any questions about the stuff that is happening there? Great. Now remind me, have we talked about interval notation in this class at all?
I do not believe so.
Cool. I'm going to do a brief intro to interval notation because that's going to lead us into next class period. Ignore the other parts of this slide. And then I'll let you guys practice the difference quotient until the end of class. And so how interval notation works is we typically in math, when we have inequalities like, I don't know, x is less than, never mind, I changed my mind. I'm going to make Rachel tell you how to do this stuff. So this is going to be section 3.1 part 2, I think. It's all stuff like the difference quotient. I mean, let's pull it up. So it isn't, because this is what we're going to cover. But like I said, I'll have Rachel cover interval notation with you guys next class period. So for the remainder of class, do 1 and 2. And if you finish 1 and 2 ahead of time, great, you can go ahead and head out early, but definitely make sure that everybody in your group is clicking with this concept. Question 1 is not too difficult. Question 2, you have to be pretty careful with your algebra because we have an x squared and a 2x. As far as kind of scaling what the difficulty will be for an exam question, I would say we got like a Goldilocks and the 3 bears situation. This question is too easy. This question is too hard. And the question I did is probably just right. So if you're curious what you should be capable of doing for the exam, something of this pace, that's not to say you shouldn't practice each of those types of questions. So are there any questions before I put you in your breakout rooms? That will be, once you complete those 2 questions, that will be class for the day. So I'm not going to put people back together. Make sure you get your homework done by the end of the night. Make sure you submit this. Maybe just submit 3.1 part 1. That's fine because that's probably where the majority of your work is. But if you want to submit both, get a little bit of feedback from Rachel when she has some time, or maybe me, maybe I'll help her catch up on grading, then submit the 3.1 part 2 as well.